طيب بسم الله الرحمن الرحيم. So last time we started to talk about the communication media. We talked about the characteristics of the different communication media, including the copper cables, the fiber optics, coaxial, things like that, and also the wireless medium and the different technologies related to each of these types of media. We also covered the core network, and we talked about the difference between circuit switching and packet switching. And we said that circuit switching establishes a virtual circuit end-to-end before starting any communication, and that's an overhead, but on the other side, it really allows us to provide high quality of service and guaranteed quality of service. But that comes with the cost of lack of scalability, because you have to really provision the resources from the beginning, even if the communication is happening, low percentage of or in low frequency of time. We also went through some motivating examples, and this was the example that we went through last time. And we said that if we have a shared channel with a maximum bandwidth of 1 megabits per second, and each of these sessions, they share this shared link, and we have n users. If we select circuit switching as the paradigm, in which case n must not exceed a 10, because we have 100 kilobits per second per user, so we cannot exceed 10 users, even if the users have active activities 10% of the time. But if we talk about packet switching, we don't have to establish a virtual circuit. We're not obligated to provide guaranteed quality of service, although, of course, in nowadays internet, we probably need to do certain level of quality of service. But there's no 100% guarantees. We cannot do this using packet switching, and we'll discuss it more today. So if we were to do that, we calculated statistically the probability that more than 10 users are sending at the same time. Why? Because if more than 10 users are sending at the same time, we go beyond the capacity of the shared link, and that might be a problem even for packet switching, right? But we said that even if that happens, we can sort of accommodate some bursty traffic even above the capacity of the link, but we have to buffer the packets at the router buffer, in which case we have to have like some kind of queuing, and that queue will have to build up, and we'll see the analysis of that further today. So we calculated the probability that more than 10 users are active, and that probability, as we said last time, is actually if we have 35 users, what is the probability of having more than 10, yani starting 11? So if we were to use I index and we have more than 10, I could be 11, 12, 13, 14, and so on, and the others are inactive, okay? So this is 35 minus I. So we can get the summation of this from I equals 11 all the way to 35, and that calculates the probability that more than 10 users are active, in which case we have the queue in the buffer or in the router will start to build up, okay? That might create a situation of panic, similar exactly to a traffic jam on the highway. So the highway usually is going smooth, but if you have any reason for traffic jam, then you start to build some traffic jams, and this traffic jam might stay for long, and everybody's frustrated and so on. So also these packets might get into the queue of the router, and then they have to build up, and then they have to wait for their turn to be processed and so on. But luckily this probability, as we said last time, is very small. So hopefully, if the probability of being active is 10%, hopefully we will not get that situation quite often, which means that the highway will still be smooth most of the time, at least 99% of the time, which is good. Okay? So does that mean that the packet switching is slam dunk winner, which means that it wins, in all aspects? Of course not, because in packet switching, providing guarantees, I shouldn't say it's impossible, it's still possible, but it's complex. Okay? In circuit switching, it's easy because you establish the circuit from the beginning and you guarantee everything. Okay? But in packet switching, it's hard. And that's why for voice calls, we usually get charged by the minute. Even if you're not talking, if you're not doing any conversation, you have to pay by the minute. Why? Because even if you're not talking, even if you're not doing any conversation, you still consume the channel, right? You still consume the channel regardless. And from 5G perspective, or from the ISP perspective, in order to give you guaranteed voice quality, they have to establish a circuit. They have to establish these resources from the beginning. Whereas the data, for data, no, we don't have to really provide delay guarantees. We don't have to really guarantee like real-time data streaming. And that's why you get charged by the packet, not by the minute, or not by the second. Okay? But the cost is that if you're watching a video on YouTube, you might get some pauses every now and then, right? Because, again, there's no guarantee. There is no established circuit. There is no delay guarantees. So packet switching is great for bursty data. It can deal with that. So even if I have more than 10 users, okay, I can still deal with bursty data, but hopefully they are all not coming at the same time. Hopefully, okay, they come and go. As long as they come every now and then, I can deal with it. But if they build up, then it's going to be a problem. Okay. It's simpler, Kaman, in the sense that I don't have to go through the overhead of building a circuit, right? So for packet switching, we don't have to dial anyone, right? We don't have to dial. We just send the packets right away from the application without having to call a person and this person has to accept. We don't have to do that. We just send, right? But it suffers from excessive congestion because we don't have control on the number of users who are concurrently sending data at the same time. That part we don't have any control for. So that's why there is a possibility, even if it's low possibility, but there is a possibility that concurrent traffic coming from users will cause what we call a congestion. Congestion is similar to traffic jam, is when the packets start to build up in the router queue, okay, and the router is not coping with the speed of the traffic that is coming from the clients or from the applications. So this is a $1 million question. So can we, in fact, provide circuit-like quality of service on packet switching? So we cannot say 100% yes, and we cannot say 100% no. This is a big research question. You have to answer using like some experiments, and it depends highly on the context we're talking about. Okay, but there is a possibility that you can provide some quality of service guarantees in packet switching, but to a certain extent. To a certain extent. Right? Not 100% reliability or quality of service. ماشي? And that's still an unsolved problem. يعني all 90% of the research we're trying to answer different variations of this question. Because the internet nowadays is purely packet switching, right? The underneath layers are packet switching. So we can do like some reliability from the application level, and we use TCP, things like that, but TCP provides really bad performance in certain applications. So how do we resolve this, right? So we use UDP, but on top of it, we use like some other sublayers. And so there are so many variations and solutions which can provide certain level of quality of service, but definitely not 100%. The only way you can provide 100% quality of service is by provisioning enough resources from the beginning. But that's not very efficient. واضحة دي? It's not efficient from a scalability point of view because you will limit the number of users. So from the perspective of the ISP, that's not good. يعني, how come you tell me that I can only accept 10 users in the network? That limits the revenue, limits يعني, so many things in the network, and it does not really utilize the resources of the network efficiently. So the network infrastructure can carry traffic from millions of users, but we're just rejecting all these millions of users, and we say that we have to provide circuit switching because we have to provide 100% guarantees. Of course, this will limit, yani, the revenue will limit many things, right? So it's not in the benefit of the ISP to use circuit switching in any way, right? طيب, that's why we cannot have any kind of centralized control on the internet, as you can imagine. There's no way you can have centralized control on the internet because it's something that's built accumulatively, right? So we cannot really afford the scenario that every single client and every single router, in order to connect to the internet, it has to have مثلا permission from XYZ organization, no matter what this organization is. We cannot do that. So we have to have some level of decentralization. Okay? So internet is built around the concept of decentralization, right? So, of course, between completely distributed and completely centralized, by the way, there are certain levels. Okay? So we can مثلا have, it's completely decentralized, but it's hierarchical, in which case the entities within the internet are actually classified into some hierarchy. So there are certain entities which are, you know, they have high infrastructure, they have enterprise routers with fiber optic cables and very, very high speed routers that support terabits per second, okay, which is طبعا obviously very expensive. And there are some other entities like QU مثلا, which have يعني less complex infrastructure. Based on that, each entity can provide certain number of users and they have certain level of scalability. يعني I cannot مثلا يعني comprehend the fact that QU, they can provide the service to 10 million users. It doesn't make any sense because the infrastructure that they have does not actually support that. So with that said, we need to have some level of decentralization, but that's exactly why the internet is what we call a roughly hierarchical. Okay, roughly hierarchical. So the way it's arranged is that we have in the core of the internet, we have the tier 1 service providers. ISP here stands for internet service providers. Internet service providers, they have very high speed infrastructures, and usually, by the way, we have around maybe 12 to 15 tier 1 service providers in the entire internet. There are طبعا, most of them are in the States, there are a few in China, things like that. Okay? Tier 1 service providers, they provide the internet service to usually, هي مش موجودة هنا بس we will see it in the next slide, to what we call tier 2 service providers. Tier 2 service providers like مثلا like Ooredoo, Vodafone, these are tier 2 service providers. So they usually have an agreement which usually involves some service level agreements, and they pay them. Okay? They pay money to them. So based on that, tier 1 service providers, they have to have some level of guarantees to tier 2 service providers. Okay? Because based on these guarantees, tier 2 service providers, they provide the service to tier 3. Okay, and this internet is roughly hierarchical into 3 layers بس, or 3 types of tiers. So tier 3 service providers are like UU مثلا, ministry. Okay, and these organizations, they have their own infrastructure that they provide direct internet service to the user. Okay, there's also in the internet, there is also the concept of a content service providers. So these content service providers, they provide not communication service, they provide contents to users, like what? Like Google, ماشي, Meta مثلا, ولا Facebook, like Netflix. Okay, so these are content service providers. Why do we call them content service providers? Because they also provide access to this content worldwide. So in order for them to do that, they have to have different servers, okay, everywhere in the world. And these servers are like gateways. And these gateways, they store content which are popular in this area. And they provision this content to a certain area. And these content servers, they have to exchange these contents every now and then in order to facilitate the access to the users. So there are 2 types of service providers. There's content distribution providers and internet service providers. Okay, and content distribution, they usually have also service level agreements with the internet service providers. So there are 2 types: content distribution and internet service providers. And the internet service providers are roughly hierarchical, organized into tiers: tier 1, tier 2, and tier 3. These are called internet exchange points. These are switches and routers which might be provisioned as a service, maybe by one organization, maybe by one institution, that, again, they don't provide direct service, but they facilitate the interconnection between the different service providers. Okay?
How does the content distribution provider work?
ما هو, as I said, يعني yes, like examples of this is like مثلا Google. In order for Google to provide مثلا YouTube service and things like that, they have to have this content stored in different data centers around the world. Okay? So the way that they provide this is that they have to have international service level agreements with the service providers of the internet. Could be tier 1 or tier 2. Based on this agreement, they can distribute their gateways in different places of the world, and that really provides good quality of service for you, because if for any video you have to fetch this video from the States and from the States only, then in many cases you will find very long latency, right? The delays will be very high, okay? But if they have a gateway which is closer, which covers مثلا MENA region, or covers certain country, or this and that, the delays you experience will be much less. And that's how they gain their credibility and their quality of service, right?
To do with like the idea that, for example, if I'm watching some TV shows that are available in Qatar, like on Netflix or something, and I travel somewhere else, they also have a different collection of movies or TV shows.
لا, these are restrictions. These are يعني service restrictions which they provide to different countries. But يعني مثلا they could have one gateway that covers all the MENA region, and within that gateway there are content that is accessed commonly in this region.
Right.
But within this region, if you try مثلا from Qatar to access this content, they tell you لا, it's restricted in your country. Okay? So it's slightly different, because what you're talking about is service level restrictions from the user level or from the application level. That's a little bit different. Here, we're talking about how the content is physically stored in the internet infrastructure. Okay? That's different from this. One concept here is so we have, as we said, we have the tier 1 service providers and tier 3, all the way to tier 3, and we have the content distributors. One concept which is really key, which is what we call multi-homing. Okay? For multi-homing here, يعني مثلا let's say QU. Okay? QU as a tier 3 service provider, they have to be attached to either directly to tier 1 or to tier 2, okay? So there is no restriction that tier 3 can get the service directly from tier 1 or from tier 2. But actually, sometimes connecting to one service provider only might not give you the level of quality of service that you want. So you could actually connect to 2 service providers, in which case you have to have service level agreement with 2 service providers at the same time. What is the benefit of this? Huh? Redundancy. Redundancy here means what? Means if one of them is having a problem, okay, then I can still have the service through the other service provider. So, which really reduces the downtime in my network infrastructure, which is good. So that's redundancy. Another reason is that if both of them are working fine, then I can have a very high throughput, okay? Because I'm using 2 different infrastructures at the same time. And because of the fact that each service provider will have infrastructure within it, right? So the routes of the packets may experience different routes, right? So if I tell you, 2 cars are going out from QU, one is going to, both of them حتى are going to Dukhan, but one of them is smart enough to take shortcut, right? So it will go faster, right? So if you go to different route, chances are some packets will get to the destination fast. And by connecting to different infrastructure, I could have يعني concurrent transmission from 2 different network paths, which will give me higher throughput. Okay?
What if packets are dependent on each other? For example, and one arrive and
this is a protocol level issue that has to be resolved at the protocol level. We'll talk about this. Okay? Okay, so any questions here? So this is the concept of roughly hierarchical. So from any source to any destination, right? Your traffic logically passes through multiple service providers, from tier 1 to tier 2 or tier 3, okay? So you have an end-to-end route. So this end-to-end route has to be facilitated through the different tiers of service providers, which will have service level agreement between each other. I also have to say that usually within the same tier service providers, you still need to have some connection and some service level agreement, but in many cases it does not involve money. يعني مثلا tier 1 service providers, tier 1 service providers, they connect to each other, but not to provide the service to each other in the sense that one is providing the service to the other. No, it's only to facilitate different paths to the internet. Okay, your traffic passes through my infrastructure, and my traffic passes through your infrastructure. So this is like equal benefit or mutual benefit. Okay, but if we don't have this connection, then that might create some restrictions on the internet level and will not allow you to provide the same quality of service to your users as you expect, right? So within the same tier of service providers, in many cases, we are equally leveled, or we are in the same level of service providers, in which case we still need to have service level agreements, but in many cases it may not involve some money or monetary benefits. Okay? طيب, very important topic which we need to talk about today is the performance matrix. So when you have, this is very important because you will use it in assignment 1, you will use it in many ways in the project. because this is a very important aspect. When you talk about a certain network scenario, how would I know that my system or my network topology is actually working fine? So you have to have metrics, right? So you need to have metrics. So we need to talk about what are the very commonly used metrics from the network point of view. Of course, we have delay, we have packet loss, we have throughput, and so on. Especially when we talk about packet switched networks, this becomes a slightly complex topic because, again, if we're talking about circuit switching, then all these parameters become almost deterministic and fixed, خلاص, يعني, because we establish the circuit, so we know that when we send the packet from here, it will arrive here and not anywhere else. But in packet switching, if you send the packet from here, it may never arrive أصلا. The packet may never arrive أصلا لأن ما فيش circuit. There's no circuit. So the packet may loop in the network and never arrive to the destination. That's first of all. Okay? Or it may be queued in different routers and it will be dropped at certain point. Okay? Because again, the quality of service is not guaranteed. Okay? So that's why when we talk about these metrics, we very commonly talk about them from the perspective of packet switched networks. So one very important metric is the queuing delay. Of course, when we talk about delay has 4 components, which we will mention in the next slide. One very key type of delay is the queuing delay. So when the packets arrive, okay, the first thing that happens is that they get queued into the router buffer, okay? So the question is now, how can we calculate the queuing delay? The queuing delay is calculated very easy, okay? So there is an arrival time and there is exit time. So when the packet arrives to the queue, we measure the timestamp. When the packet exits the queue, we measure the timestamp. So what is the queuing delay? It's actually the exit time minus the arrival time. Okay? So calculating it is easy, but is it something deterministic, which means that it has a value which never changes throughout the time?
No.
Why?
Because it depends on how much traffic is.
Right. So the arrival time, we know that because we put the packet in the router, so we know that. But the exit time, we can never know when it's going to exit because this highly depends on how many packets exist currently in the router. طب can we control the number of packets in the router? How?
We limit it like a threshold.
وبعدين?
We don't receive any packets.
طيب يعني which means that you have a maximum queue length. So you restrict them, but you don't have a minimum queue length, which means that the queue length varies throughout the time. If the queue length varies throughout the time, so is the queuing delay, right? Because what we know is somewhat deterministic is the service time of the packet. So when the packet arrives to the queue, to the head of the queue, okay, it's now the turn of this packet to be processed. Processed معناها إيه? This packet will have to be fetched from the buffer, and then I will start to transmit this packet over the link. And transmission here means that first I have to process it. Process معناها إيه? Process معناها I have to check the header. What is the destination? I can calculate the route. Okay, is the route exist? Is everything fine? Is the packet actually corrupted or not? Okay, so I have to do so many checks on the packet and the route that the packet should go through. The route معناها بس the final destination. Of course, I don't control every single point that the packet has to go through, because this can only be done using circuit. But I don't have control, right? If everything is well, then I start to transmit the packet. Transmit معناها إيه? Transmit. What do I do in order to transmit the packet? I need to convert the digital content of this packet, the ones and zeros, into a digital signal first, okay? And then I convert it into an analog signal based on baseband transmission or broadband transmission. We talked about this before. If it's a copper cable, we commonly use baseband transmission, unless we're talking about cable TV, because cable TV involves a broadband transmission, right? If we talk about wireless, in many cases we're talking about broadband transmission. So the time when you start fetching the packet and you finish processing it, and then you put it as an analog signal on the line, we call this transmission delay, okay? And that usually depends, the transmission delay is simply it depends on the length of the packet and the capacity of the line, or the rate, okay? So is that deterministic or not? Well, in many cases we can say it's deterministic if that rate is fixed. Because the length is fixed, طبعا. Length of the packet is fixed, right? You know that, right? But the rate, is it really fixed? If the rate is fixed, then the transmission time is deterministic, which means that it does not vary over time, okay? But queuing cannot be deterministic. It cannot be fixed, because we cannot control how many packets exist in the queue at any point of time. واضح? Okay, we'll reiterate on this in the coming slides. يعني. طيب, so we know now that transmission delay can be considered deterministic, although in some cases it's not, especially in wireless. And we know that queuing delay in general is probabilistic. The opposite of deterministic is probabilistic. معناها, we can say that the queuing delay on average is this, but we cannot say that it's this and it's fixed. We cannot do this, okay? طيب, the other question is, if the packets that are coming in, they start to queue, and as you said, at the end, we may have a limit to how many packets we can store in the buffer, okay? What if we hit this? Namely, this actually happens in real life. So you get to the highway, okay? Usually in the highway, things are smooth, and then you get to some place, and then you see traffic jams, right? So you wait for the traffic jams to clear, and nothing seems to be clearing, okay? I hope that doesn't happen today. But يعني, it starts to jam. But there is a limit, okay? So in some cases, you see some people are standing in the entrance of the highway, and they directory in other ways, صح? So this is similar to like packet drop. روح حتة تانية يعني. We cannot really accommodate more than this, right? Because we have a limited buffer. So at some point, we have to make a decision, and in some cases, very harsh decision, that we have to drop, okay? طيب. Okay, so we know that. So we know that we have a queue, okay? We know that this queue is full, right? So all of these are packets, okay? And the queue is currently full, okay? But we have a packet coming in. What do we do? Eh? We drop. Which packet should we drop?
The one that's been there the longest,
The
maybe?
first one, yes.
The one that's been there the longest, maybe?
The one that
No,
causes
your
this
queue
traffic.
is full.
أو بقى شفت يعني there are multiple answers now. All of them are possible answers, by the way. All of these are possible answers.
So you will drop one of those, so you will drop the new one which is coming.
Oh, that's the question. That's why I'm asking. I'm asking you now. Okay? What do you think? Okay? طيب. We need to look at it back from an analytical point of view. Okay? What is the pros and cons for... Because all the answers are valid, by the way. Okay? But what is the benefit and what is the disadvantage of each one? The easiest thing is that this is the newcomer, drop it. خلاص مش عايز صداع. The good thing about this is that this is called drop tail, by the way. This is what you will use in the assignment. In the assignment 1, you will use drop tail. And by the way, in many cases we use this on the internet. Why? Because you might think, why especially this packet يعني? Why especially this packet يعني? Well, there are some other packets in the queue, okay? Why this packet? Because it's the simplest, okay? Because if we decide to drop one of the packets in the queue, the next question is which one?
So many options.
There's so many options. So drop tail is O of 1, okay? بينما dropping any packet in the queue is
QN.
O of n. ماشي؟ O هنا اللي هي ايه complexity يعني the complexity. If I have to drop one packet in the queue, then I have to say this one no, this one no, this one no, this one no. So I have to go through all of them until I find the packet that I want to drop. And as you said, it could be the مثلا packet coming from a low priority application. Coming from Abdullah, أنا ما بحبش Abdullah, I will drop the packet coming from Abdullah's application. مثلا, okay? Or Abdullah's application is the most important. There's no way I can drop it. Okay? So I can be selective and drop one certain packet in the queue, but in that case, the complexity is high. So the good thing about drop tail is that it's very simple. It's O of 1. I don't have to look for anything, right? Another strategy, which برضو O of 1, is drop random packets. Okay? So toss a number 10. Okay, so packet number 10, drop it and put this packet instead. The good thing about random number, by the way, it has a benefit that it has some kind of fairness. Because if you try to draw a random number, chances are it can drop packet from any application. Okay? But if I drop tail, there is a chance that there is a burst coming from the same application and I drop all the packets all at once, which might not be fair to that application. But if you drop random packets, okay, that should provide better fairness because it does not designate a certain application and say I will have to drop from that application. You can drop from one application at different times. So overall, over a long period of time, you should be more fair to the different applications. And it's still O of 1. So all of these are different strategies, okay? يعني one study could be to study actually the different strategies for packet drop in the router queue. Let alone that some routers, they have multiple buffers, okay? So the decision becomes which queue first I should insert this packet to, and which packet I should drop from that queue, okay? And is that queue full or not? What is the possibility that if I put the packet here, this queue will fill up and this queue will not fill up? So that's what we call scheduling technique. And that could be really complex, يعني. Okay? Any questions? مفهوم ولا? Okay. So يعني in all cases, the queuing delay is not deterministic, and packet loss does not have like one fixed answer. We can drop packets using different strategies, and each strategy has its own pros and cons. So So with that said, the packet on one hub, يعني in one router, okay, we have 4 components for the delay, not just one. We talked about 2 of them, which is the transmission delay and the queuing delay, صح? But there are 2 more. We have the processing delay and the transmission delay and drop and propagation delay. Okay? So all of these 4, they constitute the total delay in one node, huh? That's why it's called the nodal delay. So if the packet passes, especially if we use store and forward in different routers through the end-to-end path, okay, one packet will encounter 4 components of the delay in one node. And then it will go to another node, it will encounter 4 delay components, and so on. Okay? طيب. As we said, processing delay is when the packet now gets stored in the buffer, and now it's the turn of this packet to be transmitted. So before transmission, we first process that packet. Okay? Process this packet includes what? Is this packet corrupted or it's not corrupted?
So,
Okay?
encryption, decryption.
Is صح if the packet, but actually we don't decrypt the packets at the router level. We don't do this. Okay? What you're saying is correct in the source and the destination, but we don't decrypt the packets inside the routers at all. But what is the final destination of the packet? And as we said in network security, we don't actually, that's why we don't encrypt the header. طبعا. The header is not encrypted. So we can check the destination. Is this destination there or it's not there? Okay? Okay? And then if the answer to all this is okay, things are fine, then we start to do the transmission. So this processing delay depends on the CPU power of the router. Okay? And usually it's in micro, if not actually nanoseconds. ماشي? And usually we neglect the processing delay because it's very fast. Okay? And in general, as we mentioned before in other courses, and distributed systems in general, processing cost is usually less than the communication cost in many ways. Okay? To process data locally is usually less complex, and that's why edge computing has gained a lot of emphasis, because edge computing promotes the processing data closer to the user before you transmit. So the more you process the data, the less you communicate, and that's what you want to do. Okay? But the problem is, I can say, طب خلاص, and I don't need to go to the cloud. I can process everything locally, okay? وخلاص, I can make the decision locally. Why do I need to rely on the cloud? Well, because in many cases, you don't have enough resources to do all the processing locally, right? And that's why you have to address the trade-off. What level of processing I can do locally, and what level of processing I cannot do, which means I have to go through the cloud. Okay? So this is always the question for edge computing. Anyway, so there is processing delay and queuing delay, which we said it's not deterministic. Once the packet gets its turn to be transmitted, so we have to take the ones and zeros in the packet, convert it to digital signal, and from digital signal to analog signal to be transmitted over the line. Okay? Once this analog signal is put on the line in any form, whether it's electromagnetic wave or it's a signal on a cable or something like this, then this signal goes through the line or the channel. Okay? There is also the propagation delay, which is what is the time that this signal, not packet by anymore, that this signal uses to go all the way to the next node. ماشي? When it arrives to this next node, what will happen? we will store the packet in the queue, and we'll start this process all over again. Okay? Yes. We have to encounter all these four delays again in the next node. Okay? Except if we're not using store and forward. The other thing. We talked about fast forwarding بالظبط. We don't have to use store and forward, in which case some of these delays will be neglected. Okay, because we deal with analog, so the propagation delay will go all the way. So propagation delay, as you can imagine, depends on what? Speed بالظبط وايه؟ والميديم ايه؟ length. برافو عليك. الميديم length بقى. Okay? Propagation معناها if I go with certain speed, how much should I take to reach to the destination? That depends on how far this destination is and what is the speed. You can think of it as a car that has been put on the beginning of the highway. And the highway is going all the way to the next node. Okay? So the car uses certain speed, okay? And the highway has a length of x. So basically the propagation delay is a x over the speed. That's it. The distance of the channel, the distance of the cable, divided by the speed. Usually this speed, if we're talking about fiber optics, this is the speed of a
Light.
speed of light. It's easy. If we're talking about copper, it's slightly less. Okay, it's slightly less. So this is what we have. So this is the speed, usually in copper. The speed of light is 3 times 10 to the power 8, and usually the speed in the copper cables is around 2 times 10 to the power 8. So what is the maximum distance of a UDP cable, by the way? حد فاكر من network 1? 100 meters. So if we divide 100 meters divided by 2 times 10 to the power 8, that should be around 0.5 microsecond. The maximum length of a cable.
The maximum propagation delay.
This is the maximum propagation delay on UDP. On UDP link, or TCP, or STP cable. UDP cable or STP cable, right? This is the copper cables. This is the or coaxial حتى. نفس الشيء. Okay? So as you can see, it's again, so in some cases, we also neglect the propagation delay. Half a microsecond is nothing. Okay? Usually, the bottleneck are a queuing delay and transmission delay. So,
Queue and process.
لا processing as we said, processing usually in some scenarios, what I'm saying might not hold true. Okay, and we'll see some examples. But in many cases, in practical scenarios on the internet, usually processing delay and propagation delay can be neglected. But transmission delay and queuing delay might be significant. When queuing delay is significant, in high traffic loads. When I have high traffic loads. Okay.
For each node, should we assume that DQ is the same? Queuing delay?
Queuing delay, eh?
For all nodes is the same?
No, you cannot. No. Each node, this is the router, okay? And this is the router. This router has 4 users. This router has 3 links. Okay? Hatta even if they have the same number of links, but the rate of the traffic coming from here is different. So each router has its own situation. And that's why in network topology we have something called queue state, similar to channel state in wireless. In wireless we have channel state. In networks we have what we call queue state برضو. It's not deterministic خالص, and they are not similar in any way.
Because I thought the packets would be here and there.
Not same packets, because you have different links and different traffic coming from different users. واضح كده؟ ماشي؟ So here فين So here, before we leave this, the transmission delay, as I said, depends on the length of the packet divided by the rate of the channel. If it's a cable, usually we have deterministic rates. Usually, يعني مثلا you have 100 megabits per second Ethernet cable. خلاص. So in that case, the transmission delay is somewhat deterministic. But in wireless, may not be the case. Depends on the channel state and so many things. There is fading, there is someone crossing by. There are so many factors that affect the rate of transmission over a wireless channel. So in that case, even the transmission delay is also not deterministic. Oh, sorry. So that's an analogy. So if I have this simple example from real life, I have a packet which contains 10 different caravan cars. Yani cars are coming كده in one unit. They are coming to a toll booth. عارفين toll booth اللي هو in the beginning of the highway. We don't have this alhamdulillah in Qatar, but يعني in many countries you go to the highway, then you stop at the gate, you have to pay something or get the permission before you get يعني it exists in many countries يعني. So here there is a service time here. Okay? So the packets are coming or the same packet with different bits. They are coming to the toll booth, right? So cars, the toll booth takes 12 seconds to service one car. Okay? And then the cars will start here, and from here they will propagate. We say they propagate on the channel. So that's quite similar to you have a burst of packets coming in. Each packet will have to spend some time to process it, okay? And then we start to put it on the line. Once we put it on the service time here includes بقى حتى transmission, including processing. And then we start to put it on the line. Once we put it on the line, it propagates. However, the key here is that what is the total time that all these cars, they go all the way to the second toll booth here? Okay? What is the total time? So this is the issue now. So given that the service time is 12 seconds, and when the car travels over the highway, they use a speed of 100 kilometers per second. Okay? Which means that in 100 kilometers per second, you have 100 kilometers per second, so the propagation or the time that this car takes to go all the way to the end of the highway is 100 kilometers divided by 100 kilometers per hour, sorry, not per second, per hour. Okay? What is that time? It's 1 hour. So the car takes 1 hour. Okay? But the key here is that pay attention to this because the service time is done once per car. صح? But when the car is here, okay, the propagation happens to all of them. صح؟ يعني I don't have to wait for one car to go all the way to here before the other car comes in. صح؟ They go all the way. All of them, they go at the same time. So the service time is 12 seconds times 10. صح؟ Okay? Plus
1 hour.
plus 1 hour اللي هي 60 so 10 seconds plus 10 divided by 60 عشان يبقى minute مثلا plus 60 minutes. ماشي؟ عشان كده هي 62 minutes. The key here is that propagation, okay, happens to all of them at the same time. I don't have to wait for one car to go all the way before I send the other one. They go all the way together. Otherwise, there is no point for the highway أصلا. One car goes on the highway at one time. ده إيه الهايواي الجميل ده. Okay? So that's the scenario. As you can see here, the bottleneck here is the propagation delay. صح? The bottleneck is, so the service time on this booth here is 12 seconds, which is very low. Okay? So in networks, this is similar to مثلا you have gigabit per second Ethernet. Okay? Which is يعني the service time, as you can see, the bandwidth of this channel is really, really high. So the transmission delay will be very, very low. So in that case, we can in fact neglect the service time, but the propagation time is really high. Okay? Propagation time is a scenario from networks is like if we're talking about satellite communication. Satellite communication, the propagation, so the wireless signal has to go all the way to the satellite and come back. صح? So in that case, the latency is really high. The propagation delay is really high. ماشي؟ طيب, if we were to make slight differences to this, if the car goes with طبعا this is a fictitious speed طبعا 1,000 kilometer per hour. Okay? 1,000 kilometer per hour. And the service time is 1 minute. Okay? So the moral of this scenario is that it tries to tell you إيه بقى? And in some cases, sometimes the service time or the transmission يعني time is actually the bottleneck, بينما propagation is really fast. صح? So here, again, the service time will the total time will be the 10 cars times 1 minute, okay, plus 100 kilometer divided by 1,000 by kilometer, which means that it becomes 0.6 minutes. So this becomes 0.6, and this is 10 minutes. So in that case, the propagation delay can be, in fact, ignored. It's not the bottleneck anymore, and that's يعني very common in the networks nowadays. You have gigabit Ethernet, where the transmission time is really small, okay, or you have 5G or 6G. The propagation time is really less, and the transmission time is really small. So the propagation time is really large, and the propagation time is the propagation time is small compared to the service time. Yes. طيب. هنا بقى there is a very interesting scenario that happens here. If each car takes 1 minute, okay, and the propagation time, خلينا نشيل ده okay. The propagation time here is 0.6. Propagation time. Propagation time هنا اللي هو 100 divided by 1,000. So 0.1 hour, 0.1 hour صح؟ 0.1 hour ماشي اللي هي 60 على 10 اللي هي 0.6. Okay. 0.6 here, if each car takes 1 minute, okay? So by the time the 6 cars will enter, okay? The 6 cars will have service time of 6 minutes, right? By that time, these 6 cars finish propagation. صح? Finish propagation. يعني the 6 cars arrived here, which means what? Which means that these 6 cars will لا ما فيش queuing هنا. The propagation. which means that these 6 cars will fill all the highway. Will fill all the highway, right? خلاص, they propagated, they went all the way to the other end, right? And the 7th car is still being processed. This scenario happens a lot in networks, that the packet itself, when you convert it to analog signal, okay, it fills the entire cable. The physical signal fills the entire cable. So the entire cable. So the analog signal actually fills the cable with one packet only. Okay, and that happens very commonly in network, and that's normal. But this scenario is a bit interesting, because before you finish the transmission of the 6 cars, they will have filled the entire line in terms of propagation, and that's still fine. Okay, because in the other scenario, we finish all the service of all the cars, and they're still on the highway, and they did not finish propagation, because it's 60 minutes scan, صح? But they are still in the beginning of the highway, they did not reach the end. But here, after 6 cars, they filled the entire line. And that really the scenario that happens more commonly in networks. That one packet gets converted to a physical signal, and it fills the entire line. ماشي?
So what's the significance of it filling the entire line? Like,
Nothing.
It affects the packets
No.
previously, no, right?
Eh?
It doesn't affect the packets that will come in after.
لا خالص, there's no effect. هو الفكرة إن when they propagate, it goes all the way to the other router, okay? And again, it takes its turn to be queued and transmit and processed and then transmitted. عادي, ما فيش مشكلة يعني. Okay? طيب, queuing delay بقى, there is بقى very important characteristics that we need to study here, because queuing delay is highly dependent on average packet arrival rate. As we said, packets might arrive with high rate or low rate, which means that if this is the time, and this is the arrival rate, A, okay? The arrival rate over time, okay, is like something like this. This is A at time T, okay? But there is an average rate. Average rate, okay? So the average rate here doesn't mean that it's deterministic. Yeah, so average معناه إيه? It might go up or down, but this is the average, okay? So the average rate, if طبعا the transmission time for a packet is L over R, right? If we multiply it by A, we get the what we call the traffic intensity. If this traffic intensity is 1, this means what? This means that the traffic that is coming in terms of aggregate rate, is really getting very, very close to the capacity of the channel, right? Is that possible in packet switching? Of course, it's possible. This is what we've been saying. So what will happen in that case? The queue will start to fill up, right? So if we were to calculate, so this is the router, since the packet coming in, this is the time of the arrival, until the packet finishes at the next router, okay? This is the time, next node, okay? So Tn minus Ta, in fact, equals to all the components that we talked about, صح? Plus transmission, plus queuing, plus propagation, right? All these 4 components, okay? But the key here is the queuing delay. This queuing delay is what's making all the problems, because it's not deterministic. So if the traffic intensity, okay, is close to R, is close to 1, which means that the total traffic that is coming in, okay, is approaching the capacity of the channel. So what will happen? The queue will start to build up. So in that case, what is the average queuing delay, or what is the total delay? The total delay, if the traffic that is coming in is approaching the capacity, the delay will start to grow exponentially in that case. Why? Because the queue length will start to grow, right? Which means that the queuing delay will start to get higher and higher and higher and higher. Then, so that's what happened here. If the traffic intensity is approaching 1, the queuing delay will start to grow exponentially in that case. And that's what happens in highways. When you have traffic jams, the cars will queue, and the problem here is that the car will queue very, very, very fast. صح? And sometimes it takes you hours to clear that traffic jam. صح? It takes you hours. Why? Because you have a deficiency of processing, and you have a queue which is very, very large, but regardless, you have to process one of them at a time. Okay? So you have a bottleneck, and you will have to spend sometimes minutes or hours to clear that traffic jam. This is the problem, and that's why the delay will start to grow exponentially. Okay? Type. There are some questions here is that the delay will start to grow exponentially. Will it grow forever? Like this? Huh?
Because we will drop.
So see that depends on whether the buffer inside the router is finite or limited or unlimited. Okay? If the buffer is unlimited, you will reach to infinity. All the packets are coming in. So if يعني بمعنى صح, this is the buffer. Okay? If the buffer length, if BL tends to infinity, the transmission delay will go to infinity. صح? It makes sense. Okay? طيب, what if the BL is limited بقى? In that case, we cannot calculate the delay. Why? Because the packets will be dropped actually. The packets will start to get dropped. Okay? The other question, so if that traffic intensity is low, okay, the average queue length is very small, صح? So the average queue delay is also small. Type, that makes sense. That's why, by the way, in Qatar here, maybe 10, 15 years back, I'm a bit old, so I live these days. So Qatar was all roundabouts. فاكرين؟ Qatar was full of roundabouts. That was not كده sporadic. لا بالعكس. Why? Because roundabouts are very efficient when the traffic load is low. When the traffic load is low, roundabouts are very efficient. Why? Because you don't have to wait. You go all the way على طول. You don't have to buffer anything. You just go straight. صح? When the traffic load is high, لا ما ينفعش. You cannot do this. Then you have to have traffic signals when off. You go, you not go كده يعني. You have to have some kind of discipline. Okay? So when L over R is approaching 1, the average queue delay is large. How large? It depends. If you have infinite buffer, it can grow. If the traffic intensity is above 1, then the transmission delay, the queuing delay might get to infinity. Okay? And in that case, you have a lot of work to clear the queue. Okay? طيب another interesting scenario بقى. So I reached to a state where the traffic rate is approaching the capacity of the channel, right? So delay started to go like this. And as you can see, it grows exponentially, right? And then the traffic load started to decrease, okay? So in which case, the queue will start to decrease, صح? The queue length. But the queue length will start to decrease slow. In which case, unfortunately بقى, the transmission delay will decrease linearly, not exponentially like the increase. Okay? That's why للأسف traffic jams are very costly, because you can wait in the traffic jam for hours, and even you can spend hours until the traffic jam is clear. Why? Because you have deficit of packets that is waiting in the queue, and each one has to be processed and stuff. So the decrease of the queue happens slowly, which means that the queuing delay will decrease, but slow, very slow. So exponential increase, but linear decrease. ماشي كده؟ Any questions? So these are all phenomena that you need to understand about the queuing delay. That's why it's very tricky to calculate. And you can, in assignment 1, you will be able to calculate the queuing delay empirically, يعني, in certain scenarios. You can calculate the queuing delay, instantaneous queuing delay. Okay? So another thing is that when I tell you, okay, calculate the لا خلينا the next لما نيجي نتكلم على الثروبوت. طيب, in that case, how do I calculate an end-to-end delay? So if this client wants to send to this node in China, how do you calculate the end-to-end delay?
You add all of them with the
Multiple by the nodes.
لا, not multiply.
It's different.
Not multiply.
You add summation.
Yes, it's actually the sum. Why? Why not multiply? Because the delay encountered here might be different from here, might be different from here, might be different from here. صح? Why?
New user is used.
Because queuing delay is different, right? So I cannot just say I calculate for one hop and multiply by the number of hops. It's not as simple as this. That's why we have to calculate at every node. Okay? So the best way, we on the internet, we use traceroute. Okay? So analytically, by the way, يعني, when you do an experiment, the way you calculate the delay is that you send a packet and you receive a reply. So you calculate the time from the instant you send the packet until you receive the reply. Okay? If you want to calculate the delay from here to here, then you calculate the round trip and you divide by 2. ماشي? So this is very common. Yeah. So the best way to calculate the delay is to calculate the time required for the round trip and then divide by 2. So the simplest way on the internet to calculate this is using a command called traceroute. So traceroute, what it does is that it's very simple. It sends the packet, and when it sends the packet to the final destination. But what it does is that it requires every single router along the path to reply with an acknowledgement. Okay? So if you run مثلا trace route to google.com, okay? So it goes to the first router, and then it asks this router, send me back a response. And it calculates this time for you. And usually for each node, it sends 3 packets. So we'll see how the output looks like now. This is the best way to calculate end-to-end delay of anything. Traceroute calculates the delay for every single hop along the route. So that tells you not only the delay, but it also gives you
Every single.
the route. صح? Because otherwise you don't know you don't know the route that the packet follows, right? But traceroute gives you this information. So it gives you the route and it gives you the end-to-end delay. Okay? So that's how it looks like. It looks complicated, but it's very simple. So this is the first router. So it goes to this node. And usually for each node, it sends 3 packets. Okay? So this is the delay of the first packet. This is the delay of the second packet. This is the delay of the third packet. Why they are not similar? Although we're talking about the same, يعني 3 different packets, but going to the same node, صح? Why they are different? Because they are sent in different times. At different times, you may encounter different delay. صح? Because from one instance of time to another, the queue length will change. صح? Wireless will have different state. You have so many factors that might vary, in which case the delay might be different. Okay? And then the second node, that's the delay for the 3 packets, and so on. And as you can see, طبعا, from one node to another, the delay keeps increasing. طبعا. That's normal. طبعا. Because in the first line, we're talking about 1 hop. Second line, we're talking about 2 hops. Third line, we're talking about 3 hops, and so on. مفهومة دي؟ مفهوم؟ طبعا here there are some in some hops it gives you like this star. This is not an indication that مثلا this router is down. No. This is an indication that this router does not provide responses for security reasons. That's all. يعني. Some routers, by the way, they block any response because if they respond, you will identify the IP of the router and you will know some information about the router. And some routers, they disable this functionality. Normally, يعني. ماشي? And as we said, when the queue builds up to some extent, and then we'll start to drop the packet. So there is packet loss. So the queue preceding the link in the buffer has finite capacity. In certain cases, by the way, sometimes when we do analytical يعني derivations, sometimes we assume that the buffer is unlimited. There's no such thing called unlimited, but in some cases we say it's too large that we can never get to the end of it. Okay? Packet arriving to a full queue, we drop. And as we said, dropping has different strategies. The simplest one is a drop tail. So we drop the packet that we cannot find the place for it in the buffer. We drop this packet and that's it. This is the simplest. Throughput is another metric which is very important. The throughput is slightly different from the bandwidth or the capacity of the channel. We studied that in Network 1. We said that there is the concept of, we have the bandwidth. The bandwidth is the theoretical limit of transmission over the medium. ماشي? This is the best case scenario. If you have a cable UDP, usually the capacity or the bandwidth is close to 100 megabits per second. ماشي? And that depends on certain calculations based on the frequency range and some line coding techniques, and they come up with this theoretical limit. But if you try to يعني, send some packets over this cable, you can never get to this bandwidth. Usually the throughput is something like this. It's below the theoretical bandwidth, okay? And in some cases, even on cables, by the way, there are slight differences. Why? On wireless, someone we can understand. Throughput it depends on so many factors. Someone is crossing by. Anything that happens, it affects wireless. Okay? So throughput in wireless is highly, highly dynamic. ماشي? But even in UDP cables, sometimes there are slight differences based on what? Based on interference coming from outside. Of course, especially because unshielded twisted pair, we don't have any protection, so the interference from outside affects the cable. So there are some slight differences in what we call the throughput. The throughput is below the theoretical bandwidth, okay, and it changes over time. This is time. ماشي كده؟ So that's why.
I just have a quick question. The point of let's say a DDoS attack is to overwhelm the bandwidth.
Right.
Okay. So not let's say consuming the resources of the router itself.
لا it's a lot more than just hitting the theoretical bandwidth. It's to cause bottlenecks in the network in all aspects. And the bottlenecks might include, of course, hitting the capacity of the wireless channel, filling the queues of the routers, okay? Jamming devices, which means wireless will jam so it causes high level of interference. All these are DDoS attacks or different types of DDoS attacks. واخد بالك من السؤال؟ فاهمس؟ DDoS attacks اللي هو distributed denial of service attacks. طيب, if the throughput is somewhat like this, there is the concept of instantaneous throughput and average throughput. Okay, so in reality, how do you calculate the throughput? How do we calculate the throughput? First, we need to ideally calculate the instantaneous throughput. This is what we call the instantaneous throughput at this point. This is the instantaneous throughput. Okay? And there is the average throughput. Okay? So this is the average throughput. How do you calculate the instantaneous throughput? أيوة, بس how do we calculate it in experiments when you have and I'm trying to really give you some help with assignment مثلا. In assignments, empirically مثلا, when we do experiments, okay, there is some traffic going on and there are some packets flowing and so on and so forth. How do you calculate the instantaneous throughput and the average throughput? So instantaneous throughput is number of packets per unit time. Okay? Number of packets sent successfully. Okay? Number of packets sent successfully times the length of the packet. طبعا. Okay? ليه بقى؟ لأن throughput هو bits per second. Okay? So the number of packets that are sent successfully, which means that they arrive to the final destination correctly. Okay? So in the final destination, you give a duration of time of 1 second. Okay? You calculate the number of packets that are arriving to that destination times the length of the packet. This will give you the instantaneous throughput in 1 second. As simple as that. Okay? So in that case, we calculate the instantaneous throughput. In 1 second, how many packets do we receive times the length of the packets? So this will give you the throughput in this particular second. Okay? How do you calculate the average?
Total packets over total time.
بس خلاص. The total packets that arrive throughout the entire simulation. Entire simulation مثلا is 1,000 seconds. What is the total number of packets that arrive successfully at the receiver in 1,000 seconds? Okay, divided by 1,000 seconds, it will give you the average throughput. اللي هو الأخضر. واضح؟ يبقى this is the difference between instantaneous throughput and average throughput. So we know now how to calculate the delay. The delay, we calculate the round trip time, okay, and then we can divide by 2. Okay, the throughput, we calculate the number of packets times L, length of the packet, in 1 second. This is instantaneous. In the entire duration of the simulation, this is a average. طيب, if we were to calculate the throughput here, and it happens to be RA, and we calculate the throughput here, which happens to be RB, okay? So from this node to this node, it's RB. From this node to this node, it's RA. So this is the achievable average rate, or the achievable average throughput in each link separately, okay? The question now is, sorry, this is RS and this is RC عشان يعني align مع terminology. طيب, if RS is less than RC, okay, what is the expected average throughput end to end? RS. Why? The slower. صح. This is perfectly right. So this means that throughput, we call it a bottleneck parameter. Bottleneck parameter. It's like exactly if you have water flowing in pipes, okay? This pipe has this thickness and this pipe has this thickness. When the water goes through this pipe, it doesn't get larger when it goes to this, صح? So it's restricted by the thickness of the thinnest pipe, صح? And that's why we call the throughput it's a bottleneck parameter. So it's limited by the smallest throughput on each link across the entire path, end to end. طب الديلي؟ Summation. Okay? So regardless, it's not the smallest by anymore, because the packet, when it goes through each link, it has to encounter a delay. And I cannot neglect all these delays except, that's why the delay, we call it a cumulative parameter. A cumulative parameter. Not a bottleneck anymore بقى. عرفنا الفرق؟ So that's a very important characteristic about the throughput. ماشي؟ طيب خلينا ناخد بريك. طيب, as we said, so the throughput is a bottleneck parameter. So if we have two links like this, okay, and RS is less than RC, so the total throughput or the end-to-end throughput is RS. If RS is more than RC, so the end-to-end throughput is RC, right? So the smallest يعني. طيب, a little bit of a trick بقى, complicated scenario. So if we have all these يعني sessions end to end, okay? So this node goes through one link with no sharing. So this is a dedicated link, and the throughput across this link is RS. Okay? And then they all share a network infrastructure with a capacity or with an average throughput of R. And then when they go to the final destinations, these links are also dedicated with a throughput RC. So what is the end-to-end throughput for one session? The smallest between what and what?
From source to destination.
What is that smallest يعني?
What is
The smallest of RS or RC or
Or
R لا R
R over all of them.
R over 10. Why? Because this R is to be shared between all these end-to-end sessions. This R is shared, but this R is dedicated, and this R is dedicated, right? So it's the minimum of RC, RS, and R divided by 10. حد مش فاهم دي جت ازاي؟ So this R is shared amongst all the 10 sessions end to end. So this part is the only part that's shared. Okay? So assuming that this R is actually shared fairly كمان. Fairly. Okay? Because in some cases it might not be fair. So assuming that, so there is an implicit assumption here that this R will be divided fairly amongst all the end-to-end sessions. In which case, the effective throughput for one session here is R divided by 10. So each session will have an effective throughput of R divided by 10. So what is the end-to-end throughput? It's the minimum of RS, RC, or R divided by 10. واضحة دي؟ واضحة؟ تمام؟ تمام. اتفضل.
Not the minimum of RS/RC plus R over 10?
لا, not plus.
Not plus.
Why plus?
Because RS will be dedicated, right? They don't share it with anyone. Or RC.
Yes, no, that's why the effective throughput here is RS عادي. Okay? And as we said, the session end-to-end, we need to select the smallest throughput across this end-to-end session. So part of the session is dedicated, صح, so RC or RS. And here it's dedicated, so RC. But this part is shared.
Yeah.
So it's the smallest amongst all of them. So since this is shared, so the effective throughput for one session is that we have to divide R by 10, right? So the end-to-end throughput becomes the minimum of all these three values. واضح? So that's why we call the throughput a bottleneck parameter. The last topic in this chapter is what we call protocol layers. As we all know, and as we can imagine, network function in general is very complex. It's very complex. We cannot just design the network functions in one unit كده. يعني one function from the application layer send a packet. It's one body of big function كبيرة, and then the end of the function, the packet becomes physical signal over the line. يعني one big huge function. Okay? In that case, we have to, يعني this function has to be extremely complex. Okay? But we don't do this. We have to divide the network functions into pieces. Okay? Units. In networks, we call that layers. So we have to divide the network function into layers. Why do we have to do this? There are very important reasons why we need to do this. So that's why يعني, we have network devices like hosts. The host performs more network functions compared to the router. Okay? Router does less function but more complex. Switches, they will perform less function compared to routers. Hubs, they perform less function compared to switches and so on. Okay? So that's one of the reasons that we have to actually divide the network function, because not all devices are similar. Not all devices are similar. Some will perform low or less complex network function compared to others. And depending on the type, you perform less or more network functions. What really controls that is what we call the protocol. The protocol, as we said before, set of rules that govern the communication. And usually, we have different protocols for each layer. So we said that we divide the network function into layers, and each protocol will define the rules in one layer only. Okay? So in that case, the network function will be divided into layers, and each layer we have one or more protocol. Okay? So far we know how we divide the network function. But why layers? That's what we need to understand here. Okay? So this is an analogy that will give you some idea why do we have to divide the network function into layers. Imagine like a scenario where you want to travel from one country to another. So you get to the airport, the first thing you do is that you have to enter the gate, you have to go to ticketing, check in your luggage, and then you go to from ticketing to check in your luggage, and then after that you go to the gate, and after this you go to the runway, low propagation, okay, and then you fly, the aeroplane will fly, it will go to the other end. Here it's analog signal. You can think of it, the network is analog signal. It travels, it goes, it propagates across the medium, and then it goes on the other country. You have to do the reverse operation of all of this, okay? Why do we have to do this? If you check this scenario, you will see that in each of these stages, you will see that there is quite a bit of independence. The ticketing is slightly independent from the gates, is slightly independent from the runway. The people who run this are different from the people who run this. And in some cases, you can subcontract one company to be focused on certain stage, but they are not involved in other stage. That's what happens in real life, okay? So dividing a complex function into smaller pieces is like, it follows the principle of a divide and conquer, okay? You have a very, very complex problem, okay? You want to devise a solution, you want to design a solution, but the solution, in order to define or design a solution for this problem, break down the problem into smaller problems. Each of these smaller problems can be solved efficiently, okay? So you have different people focusing on solving each small problem, okay? And in that case, you can have small or medium-sized companies who focus on solutions in one stage or one layer. So this fosters the competition between all the companies. Okay? So we see we see Cisco. Okay? مش عايز اقول هواوي, Huawei they are all over the place. But Cisco they focus on network layer. So they design routers. So they know very well how to design routers. They focus on protocols, techniques, things like that, in the network layer. They don't really focus so much on application layer. ماشي? On the other side, you see a company like Qualcomm, like AT&T, like they focus on wireless communication and providing wireless services. So they focus on the telecommunication part. In other words, physical layer. They focus on physical layer. They deal with RF radio frequency and they regulate frequencies. And so they work on this and they don't care about streaming, applications, content. They don't care about this. Okay? So you rarely have one vendor or one company that focuses on all the layers because it's highly complex. Okay? They will not be able to innovate in all these layers. So if you focus on smaller problems, you can have better and more efficient innovations in that part. Okay? But that's not the only reason. So the first reason is you have different heterogeneous devices that implement part of this function. Second, you have different vendors focusing on certain layers, in which case you foster competition. Okay? You can have better innovation if you break down the big problem into smaller problems. Another very, very important characteristic in the layered structure of the network is the isolation between the layers. There is quite a bit of isolation. Isolation here means what? Means that, and this is actually, that goes aligned with the competition part, because if you have companies that focus on one layer at a time, okay, this means that they can innovate asynchronously. They can come up with solutions in certain layer, okay? If there is no isolation between the layers, they will affect each other. There will be some conflicts. صح? Okay? So you have upgrade for the router. All of a sudden, you see the entire internet is down. And can you imagine this scenario happens? Cannot happen, right? On the contrary, you have Cisco router working with Huawei router, working with Qualcomm base station, working with this and that, right? So you have interoperability. Very important characteristics in the layered model, okay, is the layered isolation, which facilitates interoperability between the vendors. ماشي? This is very, very important. So we have to break down the big complex problem into smaller problems to foster innovation and competition between the vendors, to focus on one layer only, okay? And to facilitate the interoperability, then we have to have isolation between the layers. So if Cisco provides new innovation in the network layer, I don't have to change the upper layers or the lower layers. ماشي? How do we do this? In order to really appreciate or visualize, how do we do this? Imagine احنا مثلا when we do programming, when we program an application, what do we do? As part of the design, we do some similar activity. What do? We break down the application into functions. Each function has a header, right? And a body which has certain code. Python بقى ولا C++ or whatever, right? Okay? So if the application is broken down into functions, that's similar to the fact that you try to solve a big problem by decomposing this big problem into smaller problems. And then each problem will be solved using one function. Then you focus on this function, and then you try to implement that function. Okay? If you have the header you call a parameter 1, parameter 2, and so on. This is what we call an interface of the function. Okay? If you change the body of the function, but you don't change the interface, do you have to change the other functions? In many cases, no. صح? That's similar to the layer independence or the layer isolation. So between the layers, you have an interface. So this interface is standardized and it's fixed. Okay? So Cisco, they can put their own innovations in the network layer, but keep the interface fixed. If that happens, then that facilitates that isolation between the layers. So Cisco can perform whatever modifications they want to do in the network layer without affecting the higher layers. واضح كده؟ مفهومة؟ So interoperability is facilitated through layer isolation. Okay? So I can have many products from multiple vendors. They can interoperate together as long as the interfaces are standardized and fixed. Okay? And we have the protocol. The protocol defines the functionality in one layer bidirectionally. So between this layer and this layer, there is a protocol that facilitates the communication across this layer. For example, we all know مثلا the transport layer. We have in the transport layer, what protocol do we have in transport layer? أيوة صحيح. I don't have to wait for seconds to hear the answer. Yeah. Okay? So TCP is the protocol that facilitates the layer communication in the transport layer. Okay? HTTP, application layer. And you have IP, network layer, and so on. So a protocol focuses on the functionality in one layer. ماشي? So there is foster competition, interoperability, layer isolation. All of these are characteristics to the layer model. So with that said, طبعا in the beginning there is the ISO. عارفين الاورجنايزيشن بتاع الايزو. ISO they defined what we call OSI reference model. OSI reference model defined or broken down the network function to 7 layers. Okay, but that faded away and it was not really used or widely received. Later on, IETF, they defined what we call the internet protocol model. So there is the protocol model. The protocol model defines only 4 layers. اللي هم ايه؟ application, transport, network layer, and اللي هم بنسميهم على بعض ايه؟ network access layer. Network access. Network access is in fact physical and data link layer. That protocol model, or sometimes they call it TCP/IP model. Okay? That protocol model was standardized worldwide. Everybody uses it. So very commonly, we use the protocol model developed by IETF, and we have 4 main layers. So modularization here talks about the layering. Modularization is, again, to divide the problem into modules. These modules could be components, could be layers, tiers, whatever, okay? So in the internet, we divide the network function into layers. So it eases the maintenance and updating the system. So any update in one layer does not affect the other layers. So that way, it becomes easier and simpler to innovate in certain layer without affecting the other layers. The condition for this is that the interface has to be fixed. That's very important. So the changes of implementation of layer service transport to rest of the transparent to the rest of this does not really influence the rest of the system. So this question is philosophical question. Is layering considered harmful in any way? I wouldn't say it's harmful, but sometimes there is small limitation in the layered model that really prevents you from getting the benefit of trying to understand how the underneath layers work. ماشي؟ يعني مثلا TCP works based on certain assumptions that the medium underneath, okay, loses packets in certain way. That assumption is not 100% true and accurate in all cases. That's why we see مثلا TCP as a protocol, it performs really bad over wireless مثلا in certain applications. Okay? But if TCP somehow has access to the wireless channel state, هتقول لي ازاي؟ Using the layered model, that's not easy. Because TCP is transport layer. Okay? Channel state is in the physical layer. Okay? And we have layer isolation. So channel state is in the physical layer. TCP is in the transport layer. So you're telling me TCP will have access to the channel state? That doesn't make sense. صح? But because of this, sometimes protocols do not perform perfectly. So there is a bit of limitation. And that's why there is a very hot research area called the cross layer. Cross layer. Cross layer is when higher layers, they get information from lower layers in order to increase the efficiency of higher layer protocols. But this is very, very special case. Very special case. ماشي? But in all cases on the internet, there is complete isolation between the layers. ماشي? So cross layers usually, even if you have to do it, you have to use it within one device only. يعني مثلا in the router, router, the network layer may have access to the channel state, but within that router. Okay, so it's localized. But it cannot be performed end-to-end by any means. ماشي? In any case, يعني, the answer to this question is really hard because it's really philosophical. Okay, so it might be yes or no. So anyway, so with these layers بقى comes also the concept of encapsulation and decapsulation. And we studied that in Network 1. So in each layer, we have to have what we call a protocol data unit. In the application layer, we call it a message. In transport layer, we call it a segment. In data link layer, we call it a datagram or a frame. صح? And then in the physical layer, finally, so this is the network layer. Sorry, اللي هي الباكيت يعني. Packet. And then in the data link layer, we call it a frame. In the physical layer, what do we call it? Bits, خلاص. Or signal, actually. It's an analog signal, خلاص. ماشي? So this is what we call the protocol data unit. So the source usually has all the layers. Okay? These are 5, but if we combine those two in the network access layer, that aligns with the TCP/IP model or the protocol model. Okay? So from one layer to another, you have to perform what we call encapsulation. So you can think of encapsulation as, مثلا, if we were to send a mail يعني. Maybe we don't use frequently the mail system now, but if we use مثلا mail, imagine that you want to ship something, okay? So it goes to the first, in your house, what do? You get the product or the item, you put it in a box, you send it to the service provider, مثلا FedEx or whatever, DHL, or what do? They get this shipment and they have to put it in another box to put their labels and everything. How do they send it and so on, okay? And then it goes to another office that might provide another service, for example, مثلا mail forwarding. So you send it to Houston and they have to forward it to Qatar مثلا. So they have to also put the box in another box and so on. So this is a process of encapsulation. So when it arrives to you, you have to do the decapsulation. You open a box, you get the box, you open the box, you get the box, all the way لغاية until you get the item. That's quite similar. So this is the concept of encapsulation, and this is the concept of a decap. So at every point, you do the encapsulation, and then the frame or the segment, it goes all the way to being an analog signal. It propagates to a device, and depending on the type of the device, this could be a switch, which means that it has only two layers only. This is for the switch. Router will have 3 layers. So you could have one encapsulation and one decapsulation. Or you could have 2 levels of encapsulation and decapsulation in the case of the router. Or you could have 4 levels of decapsulation and encapsulation in case of the source or the destination. Okay? So that's how you perform the network function. Each of these headers, it will have information that is defined by the protocol. In next chapter, مثلا, for example, we'll study TCP. So we'll have to study بقى the header format for TCP, اللي هو at the segment level. What are the fields inside that segment, and why do we need to have these fields? What is the functionality of each field, and so on. ماشي? So this is the process of encapsulation and decapsulation. تمام كده? So that's the end of this chapter 1. So in this chapter we covered, and I hope we agree on certain terminology now for what is internet. It's an internetwork of networks. And we divided the internet into a network core and network edges. We talked about network edges. We talked about the issues in each one. In network edges, we talked about edge computing. We talked about the different types of access networks, the different technologies. And in the core network, we talked about packet switching and circuit switching and what are the characteristics of each one. Then we talked about the performance metrics, the data loss, the delay, the throughput, and so on. And finally, we talked about the layering model. Okay? Any questions? Okay.